All right, happy Monday, ladies and gentlemen. I apologize, I'm not there today with you guys. I think I mentioned that on Friday that I was going to be out of town. So, as you're enjoying this fine video and not getting away from me, even though I've gotten away from you, I am either sitting in an airport or probably currently on an airplane. My story is that I am learning some physics. It's really a school related trip. It was very much research intensive on the physics of airplanes. At least that's my story. I'm sticking to it. So today we are going to talk about static friction Friday. Hopefully you watched the video, or over the weekend you watched the video on kinetic friction, or for those of you in fourth hour, we actually talked about kinetic friction in class. And for those of you in 6 hour, if you have not yet watched the kinetic friction video, please go and do that first in order to understand what's going on with the static friction. It's really important to have seen that video. So I've linked that video in the description below. So if you haven't watched that, go ahead and click over to that one and then come back to this video at your leisure. So for those of you still remaining, we are talking static friction today, the force that keeps an object standing still. So if we have a box on a surface, you've likely noticed that if you try to push on an object, especially a heavy object, imagine if you're trying to move a sofa across your living room, it takes more force to get it going than it does to keep it going. Once you overcome that sort of hurdle, once you get it to budge, that it becomes easier to move, and that's due to our static friction. So similarly to kinetic friction, is our equation for static friction. This time we have the force of friction, F subscript Fr, but this time instead of having an equal sign, we have a less than or equal to the coefficient of static friction. That's the coefficient of static friction, and that is mu sub s. This time, instead of sub k for kinetic, this is sub s, and again, still times our normal force. So again, static friction. So with these two sort of types of friction, it's the same idea, but a little different application. Only one of them can act at a time. Either you're moving and you've got kinetic friction going on, or you have static friction going on and you're not moving. Again, we need two objects to be in contact. This is a contact force, but the calculations are similar, but this less than or equal to sign is going to be our big change here. I like to think of static friction as the lazier of the friction forces. It does the least amount of work possible. So when we get to a point where our force of friction is equal to mu sub n, that is our slipping point. The point when static friction stops taking effect and kinetic friction takes over. So when we're pushing with a force, when the applied force is equal to, let me write that as more of a force. When the applied force is equal to the force of, I'll call it SF, static friction, that is our slipping point. It's also the maximum that our static friction can be. Our static friction maxes out at some point, and when that happens, we have slipping. We stop being static and we actually start moving. So let me explain it a little bit better here with a diagram. Let me pull it up real quick. Let's say we had a 4 kilogram box sitting on a rough surface. Remember, rough is that idea that we do have friction, and it's being pulled by a string, so we've got some tension. A normal force, and this is a very similar box to what we've seen before, and we've got some mg, and that's going to be 40 newtons, which means that our normal force is also 40 newtons. because we're not accelerating up or down into the table or off of the table, just like we saw in the previous video. And then we'll also have some force of friction. Now we don't know at this point what that force of friction is, if it's static or kinetic. We don't know if this box is moving. It depends on what this tension is. Our type of friction depends on how much we're pushing on it. It matches up with how much we are pushing up to a point. So let me do a little work and then I'll do a little more explanation. So we're going to say our mu for static friction is going to be 0.3, decimal place there, and our mu k is going to be 0.2. Our kinetic friction, our coefficient of kinetic friction will always be smaller than our coefficient of static friction. It's impossible to have a mu sub k that is greater than mu sub s. It always takes more force to get an object moving than it does to keep it moving. It has to do with our momentum. And our force of friction from before, we saw that that is always less than or equal to mu sub s n. So that means that it is less than or equal to 0.3 times 40, which is going to be 3 out of every 10, should be 12. Yeah, 12 newtons. That is the most our friction force can be for static friction. It can be less than that, and oftentimes it will be, but the most it can possibly be is going to be 12 newtons. Let me pull some more information up here. So let's say, for instance, and I'm going to go to a new slide real quick. So again, our force of friction is less than or equal to 12. So I'm going to draw a little chart here. And we're going to have the force of tension and then our friction force. And let's say that our force of tension was 2. And here's our box. I'm going to leave off the y-axis variables. Actually, I'll just draw them in real quick. mg, and we've got our normal force, and we've got our friction, and we've got our tension. So if our tension was 2 newtons, 2 newtons is less than the 12 newtons that the friction can sort of hold. But our force of friction is not going to be 12 newtons. It's actually going to just match up whatever our tension is at that time. If our force of friction was greater, that would mean the friction was actually causing the box to move to the left, which doesn't happen. If you've just got an object sitting on the ground, let's say it's a sofa or a chair, and you're pushing on it a little bit, it doesn't start moving back the other way that you're pushing. The force of friction for static friction matches up to whatever its max is, in this case 12 newtons. That's why it's the lazy force. It does the bare minimum that it needs to stop the object from moving. So 4 newtons, our force of friction would be 4 newtons. At 11.99 newtons, we have 11.99 newtons as our force of static friction. Even at 12 newtons, we're still balanced out. We're still not going to start moving. But the instant we get 12.000, an infinite number of zeros with a 1 at the end, at this point, static friction no longer applies. Now we have started the box moving. We no longer are underneath that 12 mark. We've breached it, which means that we now are using kinetic friction instead. We're going to see a major drop in our actual force of friction. So instead of dealing with our static friction, now we are dealing with kinetic friction. So we need our other equation. Our force now is equal to our mu sub k times n. So back from the previous page, I believe it was 0.2 times that 40. And that is our force of friction at this point. And 0.2 of 40 should be 8 newtons. So now any number above 12 any number greater than 12, we get 8 newtons. We drop off and then we're steady. So kinetic friction is more like the OCD cousin of static friction. It's always what it is. And it takes effect after static friction bails out. After we've gotten above static friction, then we see a drop off and then we've got a constant force. So our big problem, our big issue with these problems is going to be deciding what's happening to my box. Is it moving? Is it not moving? And a lot of the times we're going to have to decide that before we can answer larger questions. So I want to draw a little graph for you guys. I know how much you really enjoy graphs. So here are my x and y axis, and I'm going to have my applied force. In the last example, it was tension, but it could be any applied force. If I'm pushing on a box, if I'm pulling on it, whatever it is, the force that I'm trying to use to move my object. And on the y-axis, I'm going to have my force of friction. So as my applied force increases from 0, I'm dealing with static friction. So it matches it perfectly up until some point. When we get to the point where our applied force is equal to, and let me draw that all the way up. Once it's equal to mu sub s n, then we drop off immediately. We drop off immediately to whatever that force of kinetic friction is, and then it's constant the entire way. So once we hit that point, once we get beyond that point with our applied force, we drop back into kinetic friction. So all the way here, we've got a applied force that is equal to the force of friction. When that happens, we don't have any movement. So all the way up until this point up here, we can apply as much force as we want, but the static friction will balance it out and the object will not accelerate. It will not move, in fact, because in order for static friction to be taken effect, we can't have any movement. It can't even move at a constant velocity. It is standing completely still. We're still going to be using net force equals ma, everybody's favorite equation, my favorite equation. And I want to pull up one of the homework problems for us to sort of work through. I'm pretty much going to work through all of worksheet 9, number 1 for you. So if you've got that out, I don't feel like writing all of those out again, especially because my handwriting is atrocious, so you can follow along in your packet and do the work there and get a jump start on the homework for tonight. So number 1 says the diagram to the right shows a box sitting on a rough horizontal surface. Consider a situation where the mass of the box is 6, coefficient of static friction is 0.22, and the coefficient of kinetic friction is 0.32. A horizontal force T, probably some sort of tension, which can be varied. We can pull it harder or softer, I guess would be the right word, is acting on the mass. So I'm going to draw out my mass just like it's drawn in the picture. I've got some mass. That mass is sitting on some sort of surface. So I've got a normal force pointing upward, a weight pointing down, and because I'm pulling to the right, I've got a force of friction. At this point, I don't know if it's static friction or kinetic friction, but some friction force is pointing opposite of that tension. So A says if tension equals 9.2 and the box does not start moving, what's the friction force acting on the box? So just to double check to make sure that the box wouldn't move, I'm going to get my maximum for my force of static friction. So again, static friction is mu sub s times n, and if I substitute in those numbers from the problem, we had 0.22 times 60 is going to be my normal force. That's because my weight, it said was 6 and gravity is 10. And because my box is not accelerating up or down at all, this also has to equal 60 newtons. I have to have balanced forces upwards and downwards. So this is the maximum my force of static friction can be, which comes out to be 13.2. So if my tension The problem said equaled, let's see, 9.2. That is in fact lower than 13.2, which means that I do have static friction. And the static friction will match it. Whatever that tension is, my force of friction matches it, just in the opposite direction. And these are all newtons. So if my applied force, my tension, my whatever force I'm applying to the object is less than this maximum, then I've got static friction equal to that force. Next problem in there, letter B says, what's the minimum value of T that it would have to start moving? It would have to reach that slipping point we talked about. If tension equals that maximum, whenever tension equals mu sub S times N, which is also equal to the force of kinetic friction, that is when the box will start moving. That's my minimum possible. Just a hair over it. I mean, a million billion zeros with a 1 at the end gets it moving. So we just call it the exact same. So up above in that previous slide, we said that the maximum for the force of friction was 13.2. So as long as my tension, my applied force, is 13.2 as well, then I start moving and I switch over into kinetic friction. So for letter C, it says once the box begins to move, what's the minimum force that would be needed to keep it moving at a constant velocity? So for constant velocity, and again, I'm going to switch slides. So constant velocity means my acceleration has got to be 0. So net force equals ma. If my acceleration is 0, my net force is also 0. So my net force is the sum of my forces. And that, in this case, I'm not worried about the y direction, but I've got my tension pointing to the right and my force of friction moving to the left, or pushing to the left, I should say. So my sum of forces would be positive T minus my force of friction, and that's got to equal 0. So my force of friction, I believe the kinetic friction was 0.32 was my kinetic friction. So 0.32 times the normal force. Up above, we solved that to be 60 minus T equals 0. And in order to move at a constant velocity, my tension is going to be 19.2 newtons. And as I'm doing this, I'm realizing that those two numbers probably should have gotten switched. The 0.32 should be as a static friction, and the 0.22 should have been the kinetic friction. Again, kinetic friction has to be less than the static friction as far as the coefficients go, but we can still do the workout the way it is. It just doesn't make as much sort of real sense this way around. And last thing we want to do is to take letter D. What would the amount of tension be necessary to move the box to the right with a constant acceleration of 3.4 meters per second squared? So again, net force equals ma. My acceleration, it said, was 3.4, and my mass is 6, so I'll substitute those in. And again, I've got tension minus my force of friction. So I know my object is moving. It says it's accelerating. So I'm going to use my kinetic friction. My tension is what I'm looking for, so it's still a variable. But this time I've got my force of friction with my coefficient of kinetic friction times my normal force, still equaling 6 times 3.4. And when all that math gets done, multiplying the 3.2 times the 60 and the 6 times the 3.4, we are looking at, it looks like T equals 39.6 newtons. And that's all we've really got for you today. The big issue here is going to be deciding which type of friction we're using. Remember that if your applied force, your FA, whatever that is, if it's tension, if it's a push, if that is less than mu sub S times N, you've got static friction. And that static friction is equal to FA. it does the least amount of work possible to stop you from moving that object. It's not going to do any more. Once you get equal to, once FA, that applied force, is greater than or equal to mu sub S times N, you are getting into that kinetic friction. And it's not even equal to, it's just got to be straight up greater than. If it's equal, the static friction will still just barely win out in that case, and we won't have any movement. So I hope this was helpful. Again, I apologize for not being able to be there today. But again, the processes are very similar. Work through worksheet 9. It incorporates both static and kinetic friction. Some of those problems are with inclined planes, but if you're comfortable with those still from the previous unit, that won't be any problem to apply this friction to it. Remember, we're doing the same types of processes. Free body diagrams, net force equations, solve for your variable. And finishing up friction is the last thing we've really got in this unit. We're going to take some time and just tie up any loose ends. We probably won't test until next week, I wouldn't imagine. But, yeah. So, enjoy the rest of the day. Hope you all had a good weekend. And I will be back tomorrow. We'll tie up any of these loose ends. I understand that this is probably still very rocky for many of you because these videos are sort of me just talking and hoping it all comes out the right way. But again, like I said in the last video, if this is something that you found or you believe could be useful in the future for studying at home, if you would really like to see more of these videos available to you as study resources, as anything along those lines, please do let me know. I am willing. I actually had a lot of fun just doing these. They weren't too bad. This app I've got is pretty forgiving with a lot of it. So if that is the case, just let me know, and I will continue to do these as long as people are using them. I will see you folks tomorrow. Enjoy your day, and we will tie up any loose ends tomorrow.